Alright, so I will solve practice test. So I hope that you can enjoy the video during the break. The first problem in the practice test is they give you a linear transformation T from R2 to R2 such that T of 1, 0 is 1, 1, T of 0, 1 is negative 1 and 1, and they ask you to find T of 5, 1. So, how to solve this problem? You see, we know image of this vector and this vector, right? In order to find the image of this vector, we only need to express 5, 1 as a linear combination of this vector and this vector, and then we use the property of linear transformation to find T of 5, 1. Okay, let's say if I express 5 and 1 as a linear combination of 1 and 0 plus beta of 0 and 1, right? So, and then I apply T to both sides. And I have, let's say, I want to have some space for this equation. So I have T of 5, 1, actually just lambda T of 1, 0 plus beta T of 0 and 1. Makes sense? And then we have T, what is T of 1, 0? T of 1, 0 is 1, 1 in here. And what is T of 0, 1? That is negative 1 and 1. So from here, if we find lambda and beta, we just plug alpha and beta into this to find T of 5 and 1. How to solve this equation? I think that is simple. Let's say this vector is linear combination of this and this vector, right? So if we write this identity in the form of system of linear equations, we would have the following: 0 and 1, 1, 0, and 0 and 1, and then here we have 5 and 1. So from here, lambda is 5 and beta is 1. Right? So we plug 5 and 1 in here, have 5 in here, and have 1 in here. Finally, T of 5, 1. 5 minus 1 is 4, and then 5 plus 1 is 6. That's what I have. Right? That is the first question. The second question, they give you a 2 by 2 matrix, 8, 94, 92, and 1. And they ask you to find characteristic equation and all eigenvalues, eigenvectors of this matrix. So let's write 8 minus lambda, 94, 92, and 1 minus lambda, right? And find determinant. Z equal to 0. We have 8 minus lambda, 1 minus lambda. Here minus, here negative, negative positive, with minus should be negative 8, and Z equal to 0. From here I get lambda square minus 9 lambda equal to 0. Because 8 with 1 is 8, 8 minus 1 is just 0, so 8 we cancel out. And here I get lambda minus 9 equal to 0, and lambda equal to 0 or 9. So this matrix has two different eigenvalues. Let's find eigenvectors for 0. So when lambda equal to 0, I plug 0 into this matrix. I have 8, negative 4, negative 2, and 1, right? So then I will take the second row because they are, in fact they are the same, right? The first row is equal to the second row multiplied by negative 4. So from the second row, I will write negative 2x1 plus x2 equal to 0. And then I have x2 equal to 2x1. Then I can write the general solution in the form x1 and 2x1, which is 2 times of x1 and 1, 2. So this is the basics of the first eigenspace for lambda equal to 0. Similarly, you can do for 9, right? By plugging 9 into this, You get -1, -4, and then -2, -8, something like that. And you can take the first equation or second, whatever you want. That is the second question. Next question, they give you a linear transformation from P2 to P2, where P2 is the linear is vector space of all polynomials of degree less than or equal to 2. T of A0 plus A1x plus A2x squared equal to -3A1 plus 5A2 plus -4A0 plus 4A1 minus 10A2x and plus 5A2x squared. So we talked about this space several times. The space P2 is isomorphic to R3. So basically we can consider this linear transformation as a linear transformation from R3 to R3, right? So I can say T is from R3 to R3, and T of A0, A1, A2 is equal to -3A1 plus 5A2, -4A0 plus 4A1 minus 10A2, and then 5A2. Right? So this problem asks us to find all eigenvalues of this linear transformation. That means we have to find eigenvalues of the matrix for this linear transformation. So we can put out matrix from this form. The matrix looks like, here we have no zero, A0, so that means 0 in here, -3 and 5, right? And then -4 and 4, and then -10, and then 0, 0, and 5. That is the matrix for this linear transformation. So write the characteristic equation, set it equal to 0, and then find all roots. So from here I get a minus lambda I equal to negative lambda minus 3, 5, -4, 4 minus lambda, -10, and then 0, 0, 5 minus lambda. Right? Let's find determinant of this. A minus lambda I equal to. So we expand this determinant along the third row. That should be 5 minus lambda. And then determinant of negative lambda minus 3, -4, 4 minus lambda. And I have 5 minus lambda. Inside I have negative lambda with negative, so I will write lambda times lambda minus 4. Lambda times lambda minus 4 minus 12. See, minus 12. So, of course, from here we get lambda equal to 5, right? So 5 is one eigenvalue. From here I would get lambda squared minus 4 lambda minus 12 equal to 0. So you can solve this quadratic equation. You can see lambda is equal to -2. You see -2. -2 in here we have -6 means 12. 12 minus 12 is 0. And another lambda is 6. 6 times 2 minus 12 equal to 0. So this matrix has 3 different eigenvalues: -2, 5, and 6. Okay? Of course, here they ask you to find eigenvectors for all eigenvalues. I will solve for example, for lambda equal to 5. So you do for the rest. But probably on the test, I would ask you to find just eigenvectors of one eigenvalue if the matrix is 3 by 3. So let's do that for lambda equal to 5. For lambda equal to 5, I erase this. I plug 5 into this equation, into this matrix. So I have 5 in here. 4 minus 5 is -1. 5 minus 5 is 0. So we don't have the third row. That's perfect. Let's make a row reduced row echelon form of this, or maybe row echelon form. You can do that by using calculator. I would say I'll change this. I take the second and subtract to the first. I get 1, 2, and then minus 15. And here I have like 4, 1, and 10, right? 4, 1, and 10. Just multiply the second row by 91. Here I have 0, 0, 0. And then I multiply the first row by 94 and add to the second. From here I will get 1, 2, 15, and here's 0. 94 to this I get 97. 94 is 16, so that's 17 in here. 0, 0, 0. You see? Then it would divide the second row by 7. I would get -1 in here, and then here is just 10, right? So from the second equation, I write negative x2 plus 10x3 is equal to 0, or x2 is equal to 10x3, right? And then I plug x2 into the first equation. I have x1 equal to 15 x3 minus 2 x2. And what's that? That is 15 x3 minus, since x2 is 10 x3, so I have 20 x3, which is negative 5 x3. Overall, I can write a general solution of homogeneous system where this matrix is the coefficient matrix. So I have x1 is negative 5 x3, and here I have 10 x3 and then x3. I can bring x3 out, I get 95, 10, and 1. So that's what we do. Alright? So you do for the rest. The next question. They give us a matrix A, 6, 93, 92, and 1. And they ask us to find a non-singular matrix P such that A is P to negative 1, diagonal, and P, right? Or basically, you know, they ask us to diagonalize this matrix, let's say that. Let's say that. So, 5 eigenvalues, 5 eigenvectors, and if we have different eigenvectors, we said we write all eigenvectors in the column form, so we get matrix P. Let's consider 6 minus lambda minus 3, negative 2, and 1 minus lambda, and determinant equal to 0. This is characteristic polynomial, right? Equation. So from here I get lambda minus 6, lambda minus 1, minus 6 equal to 0. So lambda square minus 7 lambda, 6 with 6 will be cancelled out. It's just 0. Or lambda minus 7 equal to 0. So I have lambda equal to 0 or lambda equal to 0. For lambda equal to 0, we need to find eigenvectors. For lambda equal to 7, we also need to do that. For example, when lambda equal to 0, I plug 0 into this, I get 6, negative 3, negative 2, and 1, right? So I take the second row. I write negative 2x1 plus x2 equal to 0. From here, x2 equal to 2x1. I write x1 to x1. So the first vector I would take is 1, 2. Alright, and then the second vector. For lambda equal to 7, I plug 7 into this, I get negative 1, negative 3, negative 2, and here negative 6, right? So I'll take the first row. I will see negative x1 minus 3x2 equal to 0, or x1 equal to negative 3x2. I can write negative 3x2, x2, or from here I can get negative 3 and 1. You see, this is the second eigenvector. So now I will write them in the form of columns. I will get p equal to, from here, let's say p equal to 1, 2, and negative 3. So that's how we can diagonalize matrix A. Of course, if you connect this problem with the current topic, the topic we covered today in the class, this is not orthogonal diagonalization. In order to make orthogonal diagonalization, we need to normalize this vector and this vector, right? Not only normalize, but we need to apply Gram-Schmidt process, because this vector and this vector, it's interesting. They are not orthogonal. This is very interesting. They are not orthogonal. Let's check one more time, For lambda equal to 0, I plug 0 into this, 6, negative 3, negative 2, and 1. Yeah, so everything is good. This is 1, 2. 1 equal to 2x. So then I have x1, 2, I have 1, 2. And here, the 7, I have negative 1, negative 3. So this is 1, 3. This is negative 3, this is 1. So that's fine. Yeah, I'm correct. So, okay, next question. They give us a matrix 0, 0, 0, 9, and they ask us to check if this matrix is diagonalizable or not. So let's say the condition for matrix to be diagonalizable is that all eigenvectors are different and are linearly independent, right? So let's find all eigenvalues first, right? So I write negative lambda 0, 0, negative lambda. Here I have, oh, I'm sorry. Here I have 9 and 0 here. So here should be 9 and negative lambda. And we get lambda squared, we set equal to 0. So we have only one again, lambda equal to 0. But when you put lambda equal to 0 into this, you get what? You get 0, 0, 9, 0, right? And what does it mean? That means x2, 9, x1 plus 0, x2 equal to 0. That means x1 is 0 and x2 arbitrary. So you can write eigenvectors for 0. That is 0 and x2, and that is x2, 0 and 1. So what does it mean? This matrix has only one eigenvalue. Multiplicity of this eigenvalue is 2, but the dimension of eigenspace for that eigenvalue is equal to 1, which is less than 2. So this matrix is not diagonalizable. Okay? Next question, 6. So they give us a linear transformation from R2 to R2. And t, x, and y equal to 3x plus y, 3x plus y. And they ask us to find basics B for the domain of T such that the matrix of T relative to B is diagonal. So basically, we need to find all eigenvalues, all eigenvectors of this, right? And then since if all eigenvectors are linearly independent, they will form a basics. And then that is the basics we need, because with respect to that basics, our linear transformation will be diagonal. because the matrix is diagonal. Make sense? So let's pull out the matrix of that. The matrix looks like A equal to 3, 1, and 3, 1, right? So find all eigenvectors or eigenvalues. We need to solve 3 minus lambda. 1, 3, 1 minus lambda. We said equal to 0. That is lambda minus 3, lambda minus 1 minus 3 equal to 0. We distribute it and simplify, we get lambda squared here, -3 with lambda is -3 lambda, and then negative lambda. I have minus 4 lambda, -3 with -1 is 3, but minus 3 means 0. So I have lambda equal to 0 or lambda equal to 4. Okay? You do the same thing, put lambda equal to 0, and you substitute 0 into this. You get 3, 1, right? The second row is also 3, 1. So I take 1 equation. I have 3x1 plus x2 equal to 0. From here, I get x2 is -3x1 or x1 -3x1. The first vector is -1, -3. And then for lambda equal to 4, I plug 4 into this, I get what? I get -1 and 1, right? I have 3, -3. So let's take the first row, I have x1 equal to x2. Or the vector is 1, 1. That's it. And you see 1 and 1, 1 and -3 are linearly independent. They form basics. And with respect to these basics, the matrix of this linear transformation would be diagonal. And so that's what we need. Okay, let me make another video, because if we solve all these problems, the video is too long and I'm afraid that I cannot upload to YouTube.